8.6 Proportions and Similar Triangles. The first, this section's mainly on theorems, kind of special things that are happening in triangles with, especially with parallel lines inside of a triangle. And the first theorem says that, well, basically these triangles are going to be congruent to each other. They're not congruent, similar because of this angle, and since these lines are parallel, these corresponding angles. So we already know from previous sections that TR is going to be proportional to RQ. Well, now with this theorem, we go into a little bit more detail, and we can even say that these segments are going to be proportional. This little piece of the triangle will be proportional to this. This ratio of QT to TR will be proportional to the ratio of SU to UR. So here they set it up, RT to TQ. That ratio is going to be proportional to RU to US. And likewise, the converse is also true the other way around. So if these are proportional, this ratio proportional to this ratio, then these lines will be parallel. So solve for x, we're going to assume that these lines are parallel. And solving for x here, we got a couple options to do this, but using that last theorem, what I'm going to do is I'm going to figure out these pieces. This is 3. Well, what's this piece? Okay, so you can feel free to label everything you know when you're trying to solve one of these. This is 15. So I know the ratio of 15 to 3 is going to have to equal the ratio of 16 to x. This side to this side. Well, 15 over 3, that's the same thing as 5 over 1. So cross multiply and divide, I get 16 fifths equals x. And that's the same thing as 3. Yeah, it goes in this 16 3 times with the remainder of 1. Are these lines parallel? So we don't know. What we want to check is to see if that converse of that theorem is true. If these sides, the ratio of this side to this side, or this segment to this segment, is equal to the ratio of this segment to this segment, then they are parallel. So let's say 9 over 24. That ratio of those, does that equal? Don't know yet. 9.75 to 26. Okay, hold on a second. Okay, so one easy way to check is if you bring up your calculator, and I'm just going to go 9 divided by 24, change that to a decimal. Okay, that's 0.375, and then just see what the other one is. Okay, I could try to do that in my head, but might get a little ugly. I'd probably have to multiply that by 4 and reduce. You could reduce this by 3, but if you're not as good with your numbers, just divide them out on a calculator. They both equal 0.375. So if they're equal, then we could say, yes, the lines are parallel. The next two theorems, well, the next theorem is basically the same thing, except for we're not dealing with triangles. If you imagine extending these out, we're dealing with 3 parallel lines. But the same thing's going to happen with 3 parallel lines or 4 parallel lines, that these parts are going to be, the ratio of these segments is going to equal the ratio of these segments. So we can say U to W, that segment, to WY, is going to have to equal VX to XZ. Okay, the ratio of this segment to this segment equals the ratio of that segment to that one. And then the next theorem has to deal with when we have a triangle and a ray bisecting one of the angles. It says that the segment AD to DB, this part, the ratio of this segment to this segment is going to equal the ratio of CA to CB. Right, AD was on this triangle, so CA has to go on the top. Right, this segment to this segment, that ratio equals the ratio of the two sides. And now we can use that to answer the next two questions. How do we solve for x? Well, 6 over 9, the ratio of these two sides has to equal x over 8. Once again, I'm going to reduce, make that, divide by 3, so I get 2/3 equals x over 8. Cross multiply and divide, you get 16/3, which 3 goes in there 5 times with a remainder of 1. There's your answer for that part. And I guess we got 2 more examples left. Now solving for x. This is where it gets a little bit trickier, because if you remember that theorem, it said the ratio of this part to this part. So we're going to have to write an equation, an expression for this segment. Okay, so write an expression for this segment. And now we don't want to just introduce a new variable. We want to keep one variable in terms of, in this case, in terms of x. So if this segment's x, and I want to know what this segment is, we're going to call that since the total length is 15 and this is x, we're going to say we're going to take 15 and take away x. Whatever this segment is, we're going to take it away from x and find this segment. So now I can write a ratio x over 15 minus x. The ratio of these sides is going to equal the ratio of 3 to 17. At this point, we cross multiply. 17x equals 3 times 15 minus x, that whole quantity. 45 minus 3x equals 17x. Get my x's over there. We get 20x equals 45. Divide by 20. X equals 20 goes in there 2 whole times, and 5 20ths left, which is 1/4. And last, solve for x and y. So we're going to use similar triangles. These triangles are similar because they share an angle and the sides are parallel. So our corresponding angles are congruent. So they're similar by angle. So if this is x and this whole thing is 12, we could write an expression for this in terms of x, or the simpler thing to do, so we could call this 12 minus x and solve it like we did up here, or in earlier examples, where this ratio, the ratio of this side to this side would equal this to that. What I'm going to do is I'm going to call this whole length 10, since I know this triangle is similar to the big triangle, right, the little triangle. So 8, that side corresponds with x. That's got to equal 10 over 12. Doing it this way, I only have one variable. And this is 5/6. So cross multiply and divide. We got 48 fifths. And to solve for y, we can use the same triangle. So you don't always have to use these theorems. You can get around not using them. But sometimes they make the problem easier. Don't use the theorem to make the problem harder. That's what I'm trying to get to. To solve for y, I would say 8 corresponds with the side length 10 on the big triangle. And that and y would correspond to 9. And I set this up a little bit different than this one. Remember, one of our properties says that we can flip these two numbers around, if you were a little confused before. But setting it up like this, you're going to get the same answer. So we got 4 fifths. So 4 times 9 is 36 fifths. Okay. Get all class period to ask me questions. Make sure you do.